So we're going to start the genomic medicine and precision medicine session. Okay. We have a great panel today, and we're very excited to share some slides with you. Let me start off with just a few comments, and then my co-moderator, Ryan, is going to tag team with me, and we'll sort of do this introduction together. But let me ask a question of the audience. So if I could take a quick survey, just show your hands. How many of you have ever had to say, "I'm sorry"? "I'm sorry, we don't know what's wrong with your child." "I'm sorry, we don't know what to treat your child with." "I'm sorry, we don't know what the diagnosis is." Let's get a show of hands. There's a lot. I think this is the challenge that we're trying to solve here. Genomic medicine and precision medicine involves a lot of technologies, but in design-based thinking, we want to create solutions that address that main problem. Do we have the clicker somewhere? Yep. Clicker. Thank you. So I'll just pick it up from you. So we wanted to start off with technology, thank you, and start to think about what type of data do we need to answer those really difficult questions. I'm not going to talk about all the dimensions of information. I'm not going to talk about proteomics and transcriptomics and some of the other analytes. I'm going to focus on one technology that's really transforming medicine, and that's whole genome sequencing. We're going to talk about other types of sequencing, next generation sequencing panels and so forth, but for the most part, we're going to focus on DNA today. And we're going to focus on other technologies that support the interpretation of that DNA. So high performance computing, this is big data, and it requires big storage and analytical and computational horsepower. You can't do whole genome sequencing without a lot of computers. You also need analytics, a lot of software to help interpret that data, translate it into information and useful features that could be linked. You need to share this information, and I'll talk, that may not be intuitive, but cloud computing, the ability to network, that's going to be critical for the next 25 years. And finally, something that may be surprising to some is cognitive computing, and we'll touch on that a little later. So we start with the idea that we can start with an individual patient, and a lot of people have heard the word personalized medicine or precision medicine. It always starts with a single patient. Perhaps they have a mystery disease. Perhaps they have a difficult to treat cancer. And we use precision medicine. We profile the disease. We profile the patient at the molecular level and look for a therapeutic option. And the hope is that we can get some mechanistic understanding that leads us to that selection. Start with one patient, and we look at the universe of options. The other direction is equally important. When we're doing drug development, we're not starting with a single patient, we're starting with a single drug. And we're trying to find that cohort of patients that are going to respond. The stuff in the middle, it's the same. The molecular profiling, the technologies, the analytics, it's all the same. So one of the things that we're going to talk about as a theme here is the idea of having an ecosystem, a cloud-based something that allows us to connect those two so we can have both better care and faster cures. So a lot of this has to do with a new language. A lot of physicians and a lot of scientists did not grow up with this new language of genomics. It's a very straightforward language if you take the time to learn it, but it's also extraordinarily complex, and it has a lot of nuance, and we're still learning how to translate it. This is a picture of the Rosetta Stone. There were lost languages. Until you had two languages next to each other where you can see what the translation is, you couldn't decipher some of these languages. So we need the Rosetta Stone equivalent to translate genomic information into something useful, like mechanisms and therapeutic options. So there's a lot of prior knowledge that needs to be integrated with genomics. It's not good enough just to sequence a patient's genome. We have to integrate a lot of different data types. And I borrowed this slide from Scott Kahn at Illumina. These are the types of data sets that they've been able to integrate. So we know how proteins interact with each other. We know the pathways. We know what clinical mutations have been linked to disease. So all that prior knowledge comes to bear when it comes to interpreting these types of genomes. Finally, we don't want to just theorize about what the next 25 years looks like, we want to actually roll up our sleeves and do something. So Dr. Chang had a very interesting challenge for us. We call him Dr. AI, by the way. So he's challenging us to say, what if we can create a prototype system, a cloud-based ecosystem where we can integrate not just genomic data, but all the ancillary knowledge that's required to translate that genome into something useful so we can interpret it, so we can mine it, not just for the end of one better care, but for the end of many clinical drug development. So that's the kind of thing that we're really excited about, building these types of ecosystems, proof of concept, see if we can do it not with millions of genomes, but hundreds of genomes, and collaborating with people like Dr. Sender to say, okay, let's start with a proof of concept with hundreds of genomes and then expand out to something that could go across the entire iSpy network. So we're really excited about this type of opportunity. Let me turn it over to my co-moderator and talk about now, and again, the big data to knowledge is a theme that you're going to hear not just today, but throughout the conference. Ryan, you want to take it over?
Yeah, sure. Thank you. So my name is Ryan Taft. I'm one of the directors of scientific research at Illumina, and probably many of you have heard of Illumina, but for those of you who haven't, it's the largest provider of next-generation sequencing. I think the current estimates are about 85 to 90% of the high-throughput sequencing data is currently generated on an Illumina machine. I joined the company about 18 months ago, and as you'll see, I came to the company with really one mission, which was how do you make this kind of technology available to every child who needs a diagnosis? And that's why I've kind of given my slides here. One child, one genome, one answer. So my specialty is really focused on kids with rare genetic disorders. Often we hear that word rare, we think it's not that many kids we need to worry about, but there's about 350 million people worldwide with a rare disorder of some kind. Current estimates in the US are about 12 to 14 million people with a rare disorder of some kind. 80% of those rare disorders are genetic in origin, and 50% of those are kids. So we've got a huge population of kids with a genetic disorder. You can imagine that getting that child an accurate diagnosis early can have a huge impact on their care. The current numbers are it takes about 6 years for these kids to get a diagnosis in the UK and about 8 in the US. So this is a so-called diagnostic odyssey. And I think we're really at this inflection point in terms of the technology's ability to have an impact on those kids. And the graph at the left there kind of shows why. So the top is Moore's Law, which probably many of you have heard about. This is the so-called doubling in processing speed in a CPU about every 18 months. And the line underneath that is Flatley's Law. Jay Flatley is the CEO of Illumina. This came out of Forbes about 18 months ago. But what you can see is that the decrease in price in terms of generating genomic data is far outstripping Moore's Law. We're actually now at a point where we need CPUs to start to catch up with what we can produce in terms of genetic data. And of course, that's a huge opportunity for deploying this in the diagnosis of these kids. The first child I worked on was a little boy named Massimo. At the time, I was a really basic scientist working on epigenetics and gene expression. And Massimo's father, a guy named Steven, did something really quite incredible. This was now 4.5 years ago. They couldn't get a diagnosis for his son. They knew he had a neurological disorder, 12 months of testing, they couldn't figure it out. And so he called up Illumina and said, what's it gonna take to sequence my son? And the story he likes to tell is they put him on hold for 20 minutes while they tried to figure out who to transfer him to. Thankfully, things have gotten a little better since then. He had that genome analyzed by about 3 groups in the US, and eventually it found its way to me. We ended up reanalyzing it. I had an amazing team helping me with this effort. And I think the real take-home message here is that we went from an undiagnosed child to a disease new to medicine in 18 months. So we found the mutations that we thought were causal to his disease. We went out and found other kids that matched the phenotype and then sequenced them, found mutations in the same gene, and we knew we had a new disease in a new cohort of kids. The next thing that happened, which ended up being really important, is we ended up getting as many of those kids, their care providers, so clinicians, external care providers, hospital support staff, family members, anybody who was interested, into a room. And what happened then was we noticed that 2 of the girls who had this same condition as Massimo were doing really, really well. And so we started digging into that. Why were they doing so well? And they'd actually been misdiagnosed with another condition at 18 months of age and had been put on corticosteroids. So the first question was, what happens if we put these kids on corticosteroids, the one that hadn't been getting them? Within 3 months, Massimo stood for the first time, so he had been totally developmentally delayed. We have MRIs before and after the corticosteroid treatment, and we've now seen that not only has disease progression stopped, some regions of his brain are actually starting to regenerate. Very simple intervention, huge impact on these patients. That really opened the floodgates for me, I think, in terms of my work and in terms of the number of cases we were seeing. One of the next cases was a little girl named Miel. This was a little girl who was actually diagnosed with Lee syndrome clinically, but they needed a definitive molecular diagnosis to get her into a clinical trial. We turned that around in about 3 weeks, got her into the clinical trial, and she stabilized about 3 months later. And this is a little girl named Rosie. This case came through the clinical lab that we have at Illumina. We have a whole genome sequencing diagnostic lab that we use as proof of concept. She came through about a month ago, 2 months ago. She had been undiagnosed for 16 years. She spent 4.5 months in the NICU. Her diagnosis had changed 7 times. She had seen 12 specialists, and we were able to resolve it in about a month and a half. It was a storybook kind of interaction. We got her the diagnosis on her way to Mayo, and the clinicians were then able to put her on the right treatment. She wrote us an email and said she was able to close her mouth for the first time on her own. So I hope these stories illustrate that this isn't science fiction anymore in terms of actually deploying high-throughput whole genome sequencing for pediatric cases that need it. And so the real question now is, how do we take it to the world? And I think you're going to hear a lot about the systems we need, the community we need to build to make that happen. We're engaging in a whole bunch of clinical trials now, working with payers and providers to try and bring this to the masses as quickly as possible. My team is really trying to provide maximum output from every whole genome. How do you make sure we're getting as much information as possible out of that genome so that this time from when we're running on kind of small panels and exomes to really seeing the genome as the standard of care for these kids is as short as possible. My joke for this conference is that this better not be 2040 or I'm not doing my job. So I hope this is 2020, not 2040. So I think we've got a really bright future ahead of us, and I think genomics has a really strong potential to change the way pediatrics can perform. Thanks.
Thank you. And with that background and introduction, let's now switch over into our panelists, and we'll start with Kathy and her story. Go ahead.
Okay, so I'm Kathleen McGreevy, and I come from Meyer Children's Hospital in Florence, Italy, and I'm actually kind of a strange person to start with in the sense that I'm going to just talk for a little bit about something that you wouldn't normally think of as being associated with precision medicine, and that's narrative medicine. And this is something that we've been talking a lot about in my hospital recently when we talk about how we want to try to prepare to implement a precision medicine approach in the future. And we've been talking about not just the IT structure, not just integration with biobanks, but also the real human approach that we have with our patients. So we have this concept of narrativomics, which we've been integrating together with genomics, with proteomics, with metabolomics, and so on and so forth, to try to provide an even more precise precision medicine. There's this great quote by Brian Hurwitz and Rita Sharon about narrative medicine that says it's a means to recognize and comprehend the singular and the particular in illness, in addition to its pathological and psychological dimensions. And I think this is a really important concept because precision medicine will allow us to divide groups of patients into subpopulations, but it doesn't really allow us to actually reach the level of an individual patient. And in order to do that, we really need to consider the human aspects of the patient, their dreams, their hopes, their desires, their beliefs, their story. And in order to do this, we need narrative medicine approaches. This kind of approach has a lot of impacts. We can think about it in terms of prevention, while on one hand, precision medicine can provide us with a lot of information that allows us to identify the propensity of a patient to develop a disease before they exhibit any clinical signs and symptoms. Narrative medicine is something that allows us to really help convince that patient to affect positive changes in their behavior. Then with diagnosis, narrative medicine, understanding the patient's narratives allows us to really contextualize what's going on in their disease and to help them try to come to terms with that. Also with treatments, there's a really important concept in terms of making sure that we don't only just treat the symptoms of the person, but also make sure that we treat them in terms of the context of their entire life. And so this is a concept that we've been working on and developing in our hospital. In February, we have a conference, a new scientific humanism. In fact, Florence is the birthplace of humanism in the Renaissance. 7 chapters on narrative medicine and precision medicine, where we're going to be trying to develop these concepts a little bit further. And so if anyone would like to come to Florence to join us, you're very warmly welcome. And if not, just hope that you get in touch and leave us your ideas on this. So thanks.
That's great. Thank you. Niels.
Thank you. My name is Neil Miller. I'm the Director of Bioinformatics for the Center for Pediatric Genomic Medicine at Children's Mercy, Kansas City. And so I think I'm going to pick up my story right where Ryan left off and hopefully tell you a little bit more of the same kind of thing. Eventually, while we're... Oh, I have to click. Oh. Yeah.
The green button. The black button. The black button.
There we go. Okay. And I'm the computer guy. So a couple more statistics just to add to what Ryan was telling us about genetic disease. So these are affecting 1 in 30 individuals. They're responsible for 1 in 6 pediatric hospital admissions. And in the Kansas City area, we had about 60,000 kids born last year. 1 in 5 deaths was attributed to genetic disease. And so diagnosing these is very difficult. They're each individual disease, they're individually rare, but in general very common. So the state of genetic testing up until very recently was that a clinician would try to decide maybe which one gene should they go test for, and they would look at the kid's symptoms and try to test for that one gene, and maybe it came back positive, maybe it came back negative. The problem with that is that patients are often, one problem with that is that patients are often not very cooperative in that they didn't read the textbook and don't know exactly what symptoms they should be presenting when they're presenting with disease. And in a pediatric population, that's a particular problem. So by contrast, when we do whole genome sequencing, we're able to look at the entire genome, look at all the genes all at once. And so to illustrate that, I thought I'd show you what ended up being actually our very first 2 patients that were went through our center when we opened in 2011. And this was a 5-year-old girl and a 9-year-old girl. They're 2 sisters. They both were presenting with severe motor delay and having trouble walking. The 9-year-old sister was in a wheelchair by this time. Big button, thank you. And so they were showing cerebellar atrophy. And so on the top, you see what would be a normal child, and on the bottom, you see her cerebellum has atrophied. By the time we saw them, these kids had gone through 5 years of specialty visits. I think they'd done 35 specialty clinic visits with no molecular diagnosis, and they'd racked up over $23,000 in testing. So we took them and we did exome sequencing, which is sequencing just the 2% of the genome, that's the protein coding part. And we were actually able to find a homozygous premature stop mutation in the ATPX gene. That means they had 2 non-working copies of this gene. And with that in hand, we were able to know that means they might have a CoQ10 deficiency and prescribe them with a 16-cent a day dietary supplement to replace the deficiency. And that ended up having really effective care. It changed treatment right away. To families, it's very important that they got some kind of answer to give an end to their diagnostic odyssey, to know what to expect. So since then, we've been able to, if we contrast that initial experience, these 35 visits, more recently we had a patient, his very first visit, he ended up going into exome sequencing, $3,000 test later, we found his disease, and then we're further able to confirm that in his 2 siblings who had previously been thought to be unaffected. And we're able to do that with no muscle biopsy, which pleases mom. And then finally, we've taken this into the neonatal ICU, where we're now able to routinely turn around whole genome sequencing in 30 hours from blood to an interpreted result. And as you can imagine, this has actually had some really profound effects on the way we're able to treat the children. I won't say that there aren't difficulties. There are lots of problems in the fact that we're generating vastly more data than we're able to make sense of right now. But I think it's clear that this is going to be something that we're really going to be focusing on for at least the next 20 years. Thank you.
That's great. And is this something that you are now offering routinely? If I take the clicker.
Yeah, actually, we have just recently, in the last couple of months, launched a clinical whole genome test, in addition to a couple of smaller panels that we offer. But we're now, any physician in Children's Mercy is able to offer a whole genome and get that turned around. Usually the less rushed version of that clinical test takes more like 6 weeks to turn around. But it's now...
And you're doing the data generation internally?
Internally, yep.
That's
We have a sequencing lab internally, and then all the compute facilities internally as well.
Is it CLIA-CAP?
It is CLIA-CAP.
Excellent.
Yes, it
That's
is.
right.
Yeah.
So CLIA-CAP involves a lot of issues, and it's a good segue to Diane, who's going to talk about her experience in that realm.
Great, and good afternoon, everyone, and I hope everyone's enjoying this as much as I am. It's been very exciting, and I'm just going to talk to you about a little bit different approach. You've heard excellent information about how we use whole genome or whole exome to diagnose a child where it's completely unclear what the disease entity is. And no one's a bigger fan of whole genome than I am. We started out with whole genome. And many times we'd have a family that would present, and I wanted to give a picture that really shows the desperation that parents have after they've been dealing with a child. Here's a child that's bleeding, he has very low platelets, and he was treated in innumerable centers for a diagnosis that's common among children, something called ITP. It's an immune-mediated thrombocytopenia, low platelets. And that's not what he had, but everybody kept treating him that way. He got exposed to steroids, he received IVIG, even Rituxan. These are extremely expensive for hospitals, would work transiently and then nothing. And so when children come to us with low platelets, we know that there are inherited syndromes that can cause that. And it could be an early sign of bone marrow failure, it could be an early sign of another bleeding disorder associated with clotting proteins. And what we used to do then is, because we know, and every day, as you've heard today, that there are new genes being formed, we thought, well, let's just do whole genome. And the problem with that, when we have a very specific presentation, in this case low platelets, is that we get way too much data to analyze. Number one, we're now required to report any incidental genes. This is a term that Neil used on our telephone call the other day. I love it, the incidentalome. You find all sorts of things that may or may not really impact that child's health. Maybe it's a risk. Maybe it's, in a girl, it might be a mutation in BRCA and have all sorts of downstream issues that the family's going to have to deal with as far as risk of breast cancer. So we wanted to just focus on the disease. That was way too much data to analyze. And we are a CAP CLIA lab. We've been dropped in by CAP and CLIA now 3 times. And every time it's been a molecular lab that's reviewing us. So we feel really good about molecular now. And what is important is that you have to validate that all of your assays are working, and that means you have to compare it with other people. And so we were going 1 gene at a time, like everybody else. And I'll just give you an example. We've sequenced over 80% of all the people with severe factor 13 deficiency in this country. It's a rare disorder. It occurs in 1 in 2 or 3 million. And so we were a referral center. For each patient, and we did it in a most streamlined way that we could using traditional sequencing, Sanger sequencing, it would take over 2 to 3 weeks, and it cost us about $3,600 per patient. And if you figure that in thrombocytopenia, there are well over 30 genes now, every day a new gene, that can cause thrombocytopenia. This would not be cost effective for any of the insurance companies for us to send out 1 at a time, each gene being sequenced. So we decided to begin to make use of HiSeq, which is an Illumina product as well, that to look at panels using NGS or next gene NGS platforms. We were making panels that had all 30 genes on them, and we could run more than 1 patient at a time. So here's an example of one of the platforms that we've created to look at patients with rare bleeding disorders. I chose this one because we're collaborating with the CDC to validate it. With rare disorders, you have to demonstrate that you're getting the same results as somebody else. And so we created this panel. It has 25 genes on it. Excuse me, 22. We can screen 32 patients at a time, and we can read each gene that we put on there. It's both exon and intron, and upstream and downstream. Each of those genes, we can read it 50 times, so it's incredibly accurate. We can now see deletions. We can see all sorts of things that we couldn't see when we were doing Sanger sequencing. And the cost per patient is only $300. And we get information on all those genes on each patient that's run. So it's incredibly powerful, and in the case of thrombocytopenia, it allows us to make the diagnosis, to give the proper therapy, and get away from, again, an odyssey for a finding where we can now cleanly diagnose it. This can be run within a week, and we can get the data back on these patients. So we get much more data, and it really helps us with the diagnosis and therapy. It's great, and I'm hoping that at some point, one other thing I want to say before I hand this over to Lenny is that it does take the collaboration of skilled people in creating the panels. So then there are certain things that we use to draw down the genes. They're called baits. There's the informatics that supports it, and we had the good fortune of doing that with a company named ResearchDx, and they've helped us with all of our panels, and just wanted to give them the credit for that.
Diane, just as you're passing it over, just real briefly, tell us, CLIA-CAP, you need to develop standards, and those standards, you have to get external validation of your test. You mentioned you're working with the CDC. There's a lot of people that are doing CLIA-CAP here. What would you like to ask?
Yeah, I asked Spiro if I could have 10 seconds to make a pitch. I know that there are other children's hospitals that would like to do panels or whole genome, and I think one of the benefits of this, unabashedly, I'm saying we should form a network of people that are doing this work so that we can share samples and also share the data on the introns, which we have very little data on children in general. And so I take this opportunity for us to form a DNA biobank in a way, and to share our data with each other. And I hope to work with Spiro and Ryan and other people here who are interested in doing that. So thank you, Spiro.
Excellent. Okay, so last but not least, we have our genomics rock star, Lenny Sender. And Lenny, when I asked the question, I'm sorry, Lenny's one of these guys that has to say that, unfortunately, way too often, because in cancer, there's, there's certain cancers that are just really difficult to treat. That's what led him to be a rock star in genomics. And over the last 4 years, I've had the pleasure of working with him, and I'm really looking forward to your story, Lenny.
Thank you. So one of the tough parts of being a pediatric oncologist or an oncologist is two things happen to you when you're at the airport. One person says, what do? You say you're a cancer doctor. Then they say, well, my cousin, my brother, my sister has cancer. Can we ask you? But the other one, they look at you with such sadness and they say, isn't it the most depressing and sad field? And how do you cope? So the way we cope and the way I cope and the way we continue to cope is to be able to not use magical thinking about how we're going to cure the next kid when the kid has died, but to be able to say, can we use science-driven hope? Can we actually start thinking about how we give us the best precise care we can to a patient with cancer? And can we learn from every single kid that we treat? So about 4.5 years ago, when that Flatley curve came about and the price point went down, we launched the first program in the country that said we were going to care about the individual patient, that N of 1. We were going to look at the child who had relapsed, their cancer had come back. We were going to sequence them. We were going to compare it to their normal genome. We were going to do RNA sequencing as well. And we've to date done 120 some patients. We've got about 300 who've been consented. We've partnered. We realized we needed to partner. We partnered with industry. We partnered with Illumina. We partnered previously with Complete Genomics, with TGen. We partnered with the right people to be able to bring it to the patient. We got a grant from Cisco to give us a telepresence system so we can talk to our people and do molecular tumor boards. And it's been an amazing 4 years. We've learned a fortune. But I'm an impatient guy, and I'm saying I wanted to take it beyond our Children's Hospital Cancer Program. I wanted to take this to the country, and what were the barriers, and how can we actually do this? And I realized, and there were learnings that came about. So the normal way we do it is we get the patient, we consent them, we put them on a sequencer, we then get the data, we analyze the data in our knowledge networks, and we bring it back to the patient in that tumor board that you see in that telepresence. But we realized that was not scalable. The price is too high, the infrastructure is too complex, and what we needed to do is we needed to make sure that we got everyone involved. It turned out that when we get calls from our colleagues at Duke University and others, and they say to us, can you please sequence the patients? They don't have the tissue in a format that we can use to do whole genome sequencing. So out of that, we said, what are the learnings? And what can we do beyond the first 4 years? So the first thing we said is, can we create a virtual biobank? Can we create a way that every single child is biobanked? The Children's Oncology Group is starting to do that, but could we do that as well? Could we learn how to standardize and harmonize how we collected tissue? Can we actually look to see, could we do profiling? So Diane just led in with profiling is cheaper. Could we do this? Well, we actually are going to do this. We've partnered with a company called Caris Life Sciences. We're going to do 592 genes. We're going to do immunohistochemistry, fluorescent in situ hybridization. We're going to look at immune response genes. We're going to look at the normal part of the tumor under that slide, as well as the tumor itself. And we're also going to look at predictive genes. And we're going to try and do it in 2,000 patients in 1 year. That is 20% of all the solid tumors. So we're building a center of excellence. The Center of Excellence is going to be throughout the country. We're going to free the data. We're going to make sure that this data is made available to everyone. We were part of the governor's initiative called, in the state of California, the California Initiative to Advance Precision Medicine, with my colleagues at UC Santa Cruz, David Hausler, Ted Goldstein. We have created an infrastructure to do this. We are going to do this across the country, nationwide, and hopefully even globally. Our goal is kids are dying today. We have technology. We can start doing it. At the same time, we're going to teach our pathologists how to store tissue outside of formalin in fresh frozen, so we can do whole genome sequencing. And then we're going to go back to people like the Illumina folk and say, can that flatly curve get a little lower? So then we can go back to whole genome sequencing. So I think that the future is bright. We're going to learn. We need to learn. And we're putting this into an open source. We're going to mine this data. We're going to put it into those cognitive learning assays. So stay tuned.
It's fantastic, Lenny. Thank you.